Thank you. Okay, page 305. Radiation. Right? First thing you must know what is radiation. Transfer of thermal energy or heat energy from a body to its surrounding in the form of electromagnetic radiation. So any hot body, whether yourself or the sun or something that heat it up, will give out radiation. And that radiation is in the form of electromagnetic radiation.
So that means we or the sun can give out radiation lah.
Yes, yes.
Okay. Alright.
Radiation from the sun reaches us through vacuum, right? Go from the sun to vacuum to earth by electromagnetic radiation. All bodies emit radiation. All bodies whose temperature is above 0 Kelvin emits thermal radiation. As long
Heat
as
radiation.
so it depends on the energy, that's all. So bodies at low temperature emits radiation of low wavelength in the infrared region. So for us, our body will emit infrared. Bodies at high temperature emits radiation in the visible and ultraviolet radiation, depending on the temperature. Okay.
Bodies at low level. So what's the two difference? The body at low temperature, body at high temperature. I don't get that part.
Higher temperature, the radiation given out is different region of the electromagnetic spectrum.
Oh,
So
this one memorize only lah.
Higher temperature, it carries more energy.
There's nothing to understand here.
Memory only, memorize only. This is your what I call it, your SPM work. Right? That's your electromagnetic radiation. That's your third semester work.
Yeah, the wavelength one. The
infrared is here. So our body probably emit here, this region. Longer wavelength of the infrared. Longer wavelength, the smaller the energy carry. Right? Or if you want this one, you study in third semester. Energy of photon, we call it photon rather than wave lah. Right? If you don't confuse yourself, just take that the energy equals to H times F. H is a constant called Planck's constant. F
this is chemistry also, they got larger.
It means higher frequency, higher energy. That's all. That will help you lah. I don't need to memorize the formula. That one we study in the third semester.
Sorry, which one again?
So it means that the hotter body emits radiation of higher frequency. Higher frequency carry more energy. Ours one, infrared, lower energy, lower frequency. Because our body temperature is lower. Okay with that?
Wait, so we carry longer wavelength lah, right?
Yeah, longer wavelength, infrared. Our body emit infrared.
I mean infrared.
So all these got higher energy, gamma ray, X-ray, and ultraviolet, higher energy than infrared.
Yeah, because infrared's wavelength is longer, but that's why it's smaller. But those left ones are smaller wavelengths. That's why more energy
region, right? Like this one towards the visible region have more energy than the one further down near the radio wave there.
So it depends.
Okay,
So that means if it's low means right. So that means if it's low means it will go towards the visible light lah.
No.
No.
Low temperature infrared. Low temperature infrared.
No, because this one they put the wavelength and energy. Temperature I can't determine it.
Longer wavelength, smaller frequency. That's your STM work. C, speed of light equals to HF, C equals to HF. Sorry, C equals to lambda F. Yeah?
Lambda F. Yeah, okay.
This your C equals to lambda F is written there. Right? Higher frequency, lower wavelength. This is your SPM work. Measuring radiation, number 5 in your book. Human skin is quite sensitive to thermal radiation. We can feel it. That's why when you stand,
I mean the sun, right, sir?
you can feel the sun's heat. Or you stand near a fire, you can feel the radiation. Right? If you stand too close. Instruments that are used to measure thermal radiation are mercury thermometer with blackened bulb. We just blacken the bulb. Blacken it so they can absorb radiation. Bolometer, thermopile. Right? Let's look at barometer for measuring radiation. Right? This is your absorbing conductor, that one, wavy shape. And then there's your dielectric material, or insulator if you like. Then you got your incident light. Right? So a bolometer is an instrument to measure thermal radiation. It consists of narrow strip of platinum. So these are conductors made of platinum with surface blackened. Important, blackened, they can absorb radiation. Blackened surface is a good absorber of thermal radiation. Thermal radiation falling on the bolometer causes its temperature and resistance to increase. Right? Remember, temperature increase, resistance of conductor will increase. That one is your next.
Not decrease, man.
No, no. The molecules vibrate faster, so the electron will have more difficulty flowing through. That's why the resistance increases. That's your next semester's work.
Oh, so this one just accept it only lah.
You have studied in your SPM. Resistance increases with temperature.
Oh yeah, sorry, I forgot.
Then you can put your ammeter and voltmeter there to measure the resistance. Okay. Thermopile. Right? What is thermopile? Composed of several thermocouples. Two connected in series. Each thermocouple consists of a strip of bismuth and a strip of antimony. That's your antimony. Okay. This is bismuth, antimony, bismuth, antimony, bismuth.
Antimony means it's the one white, right? Surrounding white.
Yeah. Don't bother about it. Just know that it's two different metals joined together. That's all.
Bismuth is black, antimony is white. Okay.
One junction of thermocouple is exposed. So this is one junction. That's the other junction. So this junction is exposed to this incident radiation. That one is a shield, protect it from any radiation. So this one is a low temperature.
Protect it from what radiation again?
We don't want any radiation from the back.
Oh, you only want from the
only
front.
One direction only. Temperature hot junction increases. This is a hot junction. This is a hot junction. This is a cold junction. Temperature difference between the hot and cold junction produce an EMF, which is measured by a millivoltmeter. So you can either use a galvanometer to measure current or millivoltmeter to measure the voltage, potential difference. Okay.
Okay.
Then you can convert to temperature. Okay. Stevens-Boltzmann's law, page 306, number 1. Memorize it, this law. Energy radiated by a body per second, or the radiated power, is proportional to the surface area, the nature of the surface, and to the fourth power absolute temperature. Summarize it with that equation. P equals to E sigma A T to the power 4. That's your thermal electromagnetic radiation from the sun. So P is the power radiated, or energy radiated per second. E is the emissivity of the surface. T T is the absolute temperature. A is the surface area. Remember, A is surface area. And then sigma is given in your formula sheet. Right? You have to use your formula sheet to find the value. It's a constant value. Okay with that?
Yeah, just 1 second.
No need to memorize. Know where to get it from the data sheet. It's all in your book, page 306, number 1.
Yeah, it's on the slide also. I got it. Yeah, it's from the book.
Okay.
Okay.
So the value of E is between 0 and 1. 1 for perfect emitter. For perfect radiator. That means a black body lah.
Perfect radiator means black body.
Black body lah. It absorbs all the radiation. It also emits all the radiation. Okay, if that's your body, this one, that's your body. Net power radiation radiated, number 2 in your note. A body absorbs radiation from its surrounding of temperature T0. Right, there's a T0, surrounding temperature. It also radiates to the surrounding. So the net power radiated, that's your body. This one, that's your body. Temperature is T. So the body has a higher temperature than the surrounding. So it will be a net emitter. Right? So it means irradiation. So that's the formula you use. You just add another T naught square to the power 4, that's all. Same formula as before. Net power radiated, temperature of body, temperature of surrounding. Okay. Memorize only and know how to use the formula. As I say, you don't do past year paper, you cannot memorize the formula one. Don't know how to use the formula also. That's why you must try the question.
Okay.
So when will be your next class? When do you want the next class?
Next Saturday.
Next Saturday, you don't want Monday.
No, Monday got school. By the time I come back school, be very tired one.
Oh, okay.
Because I finish at 2:10. By the time I come back home, maximum also be 3 o'clock already. I drive some more.
So no other time to use during the weekdays lah. Every day come back very late lah.
Except Friday.
So you decide if you want to change the time, you let me know. If not, Saturday morning.
Friday I'll finish by 11:40.
If you want, you can have it Friday. You just think about it. Let me know if you want to change the time.
Oh, now teacher prefer weekday already lah.
Easier if you want.
Easier. Okay.
We have to do our last topic test already, which is 11, and then try the past year paper already. Cannot waste time already. Not much time already.
Okay.
That's your final area of revision. And then which area of weakness you have to ask already.
Oh, I have to start asking my weakness when I revise.
Then you can see the weakness. Where you do the question, then you will know whether you know how to do, or then you can know where is your weakness.
Okay.
Okay, so as the body loses energy, right, as your body loses energy, the temperature goes down, decreases until the temperature of the surrounding. So the hot body will keep on losing energy until the temperature becomes equal to the surrounding. That's how it loses energy, by radiation. Same value of E applies for both emission and absorption of radiation. Same E value. E is the emissivity of the body. It has the same value whether it emit or absorb. Okay with that? Memory work only, nothing to understand. Just memorize only.
E applies for both emission and absorption of radiation. So body loses energy means temperature decreases until okay. Okay, black body then.
Okay, black body is a perfect emitter. E equals to 1, number 5. Right? So, as the diagram show you, all incident radiation is absorbed. So, and then you are told the emitted radiation is only a function of the radiator's temperature. So, a perfect emitter is also a perfect absorber of radiation. Such a body is called a black body. Right? That's what physicists want. You call it a black body. You always look at ideal case. Black body is defined as a body that absorbs all electromagnetic radiation. It will emit all.
Absorbs all electromagnetic radiations.
That's why it's called a black body, no?
Yeah, because it's like perfect lah.
Perfect, no?
So I understand.
of a
That
dark
means
black
it's
body
like
is
E
close
equals
to
to
1.
1 lah. Close to 1 or equals to 1?
Close to 1. That means you can take it as 1.
Yeah lah, 1, 0.999 like that.
So experimental black body, we can have a copper sphere, a tiny hole there. Right? A fine hole is made for radiation to enter into the sphere. As shown in the diagram, it goes inside, it got reflected, and then it doesn't come out. That's what it means by a black body. It absorbs the radiation. That inside is black, so nothing comes out. In practice, a perfect black body is not available. Right? It's in our mind only. But that is nothing to stop physicists from thinking. Consider a hollow sphere coated with lamp black on its inner surface. You can use charcoal if you want to lah. Now, when radiation are made to pass through the hole, it undergoes multiple reflection and are completely absorbed. So it doesn't come out. That's what I mean by black body. They absorb the radiation. So the radiation goes in. It usually won't go in normally. It will go at different angle, and then it will be reflected inside, multiple reflection, and then finally absorbed in the body. Thus, a black body acts as a perfect absorber. That's what we want, right? Experimentally, that's our black body, a copper sphere, hollow copper sphere.
So that means in real life, there's no perfect black body.
No such thing. No such thing. We have tried to.
So that means the one just now one was theoretical lah.
Just in a physicist's mind only. What we want.
I see.
What we want. Okay.
Okay.
Ideal reflector. Emissivity equals 0. E equals to 0. Ideal reflector does not absorb any radiation. That's what it means by ideal. It reflects all radiation. Value of E for a highly polished surface is close to 0. That means very near to 0 lah. It's a poor thermal radiator and absorber. So if it's ideal reflector, it's also a poor absorber. It's also a poor radiator. Okay, don't need to bother about this one. This one is more the application in astronomy. That means if you see a star that is red, you know that's roughly the temperature. You see a yellow star, it's about 6,000 Kelvin. See a blue star, it's that temperature, 18,000 Kelvin. Right? So spectral line of thermal energy radiated by a black body has pattern of intensity of radiation over a range of wavelength or frequency depends only on its temperature. That graph basically tells you different wavelength, depends on the temperature. In astronomy, stars are often modeled as black body. That means we consider star as black body, although it is not always a good approximation. The temperature of a star can be deduced from the wavelength of the peak of the radiation of the curve. Right? We don't need to worry. Just know roughly where is the application. Okay. All we need to do is look at the peak wavelength. And then we know the temperature. That's how we relate temperature to the color. Okay, no need to worry about this one. This is application. If you want, you can read up more.
This one nothing related to the chapter, right?
Nothing. Just to tell you how we apply this knowledge that we study about radiation of a hot body. Okay, temperature of the sun. Right, this is also application, page 307. Right, this one you study in your third semester. Intensity is the rate of energy falling normally per unit area on the surface. Right, normally means perpendicular. So it's P divided by A. No? P is in watt. A is in meter square. This part also, I don't think you need to worry also. Just for your info. How we estimate the temperature of the sun, that's all. It's in your note. So unit for intensity is watt per meter square. It's a vector. It has a direction. Solar constant. Solar constant S is the average intensity of radiation of the sun on the Earth's surface. That one we can count. We can measure. The solar constant, the intensity of radiation from the sun on the Earth's surface. And this is the value, average value. And we can measure on the Earth. There's your sun there. And that's the Earth. So we can measure this value that we receive on the Earth. Intensity for a point source of light, intensity at a distance r away from the wave spread out evenly in all directions. There's your P, that's your point source. Right? The power radiator is P. It emits out evenly in all directions. So it will be a sphere. A sphere of radius. If you look at a sphere of radius r or at a distant radius r, then the intensity is just your that energy, that power divided by the surface area. So we call it an inverse square law. That means as you go further, the intensity becomes smaller and smaller. Right? R square, we call it inverse square law. Okay with that?
Intensity.
Not need to worry that much. Just understand what I'm teaching you, and then you want, you can go over the slide.
No, actually, I can't get it, lecture.
Nothing much. It's just the P divided by area. Area is the surface area of the sphere. The energy is spread over the whole surface.
So as the intensity increases, the radius decreases lah.
From the formula, further away it is, the smaller is the intensity. Okay.
Yeah. So radius decreases, intensity increases. Okay.
So temperature of sun, right? Big R is radius of the sun. S is the solar constant, right? The intensity that we measure on Earth. Small r is the average distance of the sun and the Earth. R is the intensity of the sun. So rate of energy emitted from the sun, we can treat the sun as a source of energy. That's the power. Right? Power is just 4 pi r squared times I. Okay. That's the power radiated. Then that energy will spread out over the whole sphere. That's why we calculate our 4 pi r squared times S. S is the value that we measure. That's the intensity that we measure on Earth. So intensity is R squared over R squared S. Yep. We put these two equal. Then we get this formula. Assuming that the sun is a black body with a surface temperature T, so it's P equals to 4 pi R squared. Right? We are just using Stephen's law just now. Right? There's the area, surface area. There's Stephen's constant. There's a temperature. Then our 4 pi R squared times I. Then I, we can replace it with this value. Then we can calculate our temperature. Don't bother. If you can take it. If not, just leave it there. Right? It's in your book. I just go over with you, that's all. Just to show you the application part.
Okay, I means leave it lah.
Just leave it. Just to give you a rough idea how we apply this part of Stephen's law to estimate the temperature of the sun or the temperature of
No,
stars.
sir, the theta temperature to the power of 4, right? So below that, the times R square over R
These
square
two
part, I
only,
don't
from
get
these
it.
two formula. These two formula are the same. So 4 pi R square cancel off, and this equal. These two equal. Then calculate your T.
Yes. Oh, and then just equal it lah.
Yeah, just equal, that's all. The 4 pi R square cancel off. And then you just take the sigma to the other side, it becomes down there. That's the equation the same. Then you square root to the power 4, to the root 4.
Hmm.
Okay, and then we can calculate out with all the values that we know. It's about 5,700 Kelvin. Go to your textbook, it's given you. I just go roughly with you. It's not necessary, I think. Okay,
I had a temperature of the sun. I found it.
Radiation is a transfer of thermal energy from a body to its surrounding in the form of electromagnetic radiation. Instruments are used to measure thermal radiation. Right? And then this is the formula that we need to remember how to use it. T absolute temperature. A is the surface area. Sigma is the Stephen's constant. Right? This one is usually applied for the sun only, for the hot body, that's all. No surrounding temperature involved. This one is where there's a surrounding temperature and you want to know the net power emitted. Our surface, as I said, you want to do well, you want to understand the theory, you have to apply it. So try the question in your book. So ideal reflector, E equals to 0. Black body, E equals to 1. Black body, dull black surface, also E equals to 1. Highly polished is the ideal reflector, so E equals to 0. So all these things you need to remember. Yep. And then the surface area of a sphere is 4 pi r square. Okay.
Okay.
Okay, global warming, page 309. Right, the picture will summarize for you lah.
Yep.
This don't bother about this graph. It's just to convince you that the temperature of the surface is rising.
Until now.
Global warming. Global warming is the phenomenon of increasing average air temperature near the surface of the Earth over the past 1 to 2 centuries. Climate scientists have since the mid-20th century gathered detailed observation of various weather phenomena such as temperature, precipitation means the rain, the snow, and the storm, and of related influence on climate such as ocean current and the atmosphere chemical composition. These data indicate the Earth climate has changed over almost every conceivable time scale since the beginning of geologic time, that means very long time now, and that the influence of human activity since at the beginning of industrial revolution has been deeply woven into the fabric of climate change. So it means that since the industrial revolution, human being activities has changed the climate. Okay, just for your reading. So the first thing to remember under your four, greenhouse, what is a greenhouse? A greenhouse is called a glass house, or if with sufficient heating or hot house, if you need heating. But usually greenhouse, we don't heat it up. It's a structure with walls and roof made chiefly of transparent materials such as glass, in which the plant required regulated climate conditions are grown. You want the temperature inside the glass, usually made of glass, the greenhouse. Temperature is different from outside. We can control the temperature inside. Okay, there's a greenhouse. Okay with that?
Yeah, greenhouse is like the plants where they can have their own heat. Yeah, minimal this one.
Where you see is made of glass or special material. You want to keep
so
the
that you
temperature
can
different from outside.
so
you can
yeah,
control
the sufficient one,
inside.
like optimum one.
Okay,
Okay.
So a greenhouse temperature is warmer than outside. That's the purpose of we have a greenhouse. You want a temperature different from outside. So how does it happen? Yeah, radiation of short wavelength are able to pass through the glass, right, from the sun, from the heat. Radiation, shorter wavelength, visible and ultraviolet. So shorter wavelength have greater energy. Glass is opaque to long wavelength, right? The radiation shorter wavelength can enter. Longer wavelength is the infrared. So inside there, the plants are at a lower temperature, so it emits infrared. Infrared is reflected into the greenhouse, right? So that infrared given out by the plants, the pots in the greenhouse there, it absorbs, it gives out the infrared. So the infrared is reflected within the glass, cannot come out. Air warmed by the hot interior causes temperature of greenhouse to rise. So the inside of the house, greenhouse is warmer than outside. That's why it's happening. Radiation goes in, cannot leave. Right? Enter, absorbed by the sun. The sun radiation, longer wavelength, energy absorbed by the plants, the pots. So it becomes warmer. It emits infrared. That infrared cannot leave the glass house. So it stays within the greenhouse. So it keeps the temperature higher than outside. Okay.
Okay.
That's what we have done before. Okay, I think we better take 5 minutes break. Then I'll send you a new Zoom.
Okay, sir.
Okay.